was this notion about integrality. Well, the notion of being integrally closed, being preserved in a localization. So I want to prove that. Let me remind you of the theorem. You've been leaving a really good job here. Proposition. R is a domain.
Be careful of a wrong. That's what they're probably showing.
Of course, when I say integrally closed, this sort of implies an appointment domain because we have to talk about the quotient field. And S and R is a multiple closed set. And I'm going to say S. Then R localized. Okay, so in other words, if R is integrally closed, then if you take any set of denominators, make the fractions there, then what you get is a new integrally closed domain. So suppose that A over B is in K, the quotient field. So here I'm going to assume, notice, let me make clear that the quotient field of R and the quotient field of R localized at S are the same thing because this set of fractions is still contained within the quotient field. So just to be clear about what I mean here, I do mean that A and R. And suppose, maybe I'll also call this omega here, just for ease. If omega is equal over RS, then that, let's say omega b plus Rn minus 1, Sn minus 1, omega n minus 1, 2 Sn minus 2, minus 2, R1 Sn S0, 0, with my notation, I hope it's fairly clear, Ri is in R, Si is in S. Right, so there's some equation of integrality over R localized at S, right? Oh, and our math club speaker is here today, so you all should consider coming to that. It sounds like a real fun talk. Okay, so we need to show that this omega is already in R localized at S. So what's one thing that I can do here?
B is in S.
Well, that's right. That, essentially, what I want to do is show that B is an S. Of course, let me underscore a possible hazard with this, and that is, I really want to show that omega is R localized at S. So let me do something kind of silly here. Notice B doesn't necessarily have to be an S, right? Because, for example, I could have R over S and then multiply top and bottom by the same element that may not be an S. So really, I want to show that A over B can be written as some A prime over S, right? So it's not clear that B is an S, but we need to show that we can re-engineer this. Let me tell you my usual problem here. I really do not like fractions. So I I can make this equation easier by clearing out the fractions, right? And let me just do this. Let's multiply. Let me call this T. Oops, I should have started 0, shouldn't I? That way. So that'll do the trick, right? So I'm gonna make this easier by multiplying T. So this is T omega n plus T n minus 1 omega n minus 1 plus T n minus 2 omega n minus 2 T1 omega is T0. Where each Ti is in R, correct? Because notice, this is just kind of an abbreviated way of writing Rn minus 1 times all the factors of T that don't contain n minus 1 and so forth, right?
Do you mean to say S?
No, I don't, because, so for example, this first one right here, certainly the T is an S, right? But when I hit the T here, what happens is it sweeps out Sn minus 1. But see, I've also got this back of R, so it may not be, right, after that, it may not be, but it's in R. That's good enough. Let me do a little bit more prestidigitation. I'm now gonna hit this thing with, let's multiply this by T to the n minus 1. This is a trick that we actually used in an earlier proof to get the Tn omega n plus Tn minus 1, T to the n minus 1, omega n minus 1. Yeah, that's right. Plus Tn minus 2, Tn minus 1, omega n minus 2, plus T1, Tn minus 1 omega, plus T0, Tn minus 1 is 0. And so, once again, let me do a little bit more rewriting. This is T omega to the n plus Tn minus 1, T omega 1, n minus 2, T one, T n minus 2, T omega. Right. So notice this is an equation of integrality for the element T omega. So notice that this means that T omega is integral over R. But R is integrally closed. So T omega is equal to, let me make it up, some R in R. Correct. Omega was A over B. Therefore, A over B is R over T with R and R and T and S. So A, B, RS and RS. Right. And so notice that the proof sort of rewrote our representation as it was needed. Okay, so let's talk, so I've gone over this before, we introduced this briefly. Let's start to look a little bit more in depth at this notion of valuation. Uh, let me, oh, by the way, the next homework, I might release over the weekend, maybe, but I'll do my official little kind of chit chat about it on Monday. And it won't be, it'll be due sometime after the fall break. Okay, so let's, uh, check this out here. So I'm gonna go for the, I think this is the way let me call it one. So this was kind of my first bare bones definition of evaluation domain. An integral domain E is a valuation, which you're gonna get a little bit to the bottom of this name in a bit. I mean, I don't know where this, from this definition, it's not really clear where it comes from, right? But if we're all AB, put zero if you like, we're all AB and the non-zero element is V, either A divides B or B divides A. One of those two has to happen. So this was the first definition of valuation that I gave you. Let me first give you some properties. And we've seen some of this before. If V is a valuation domain, then it enjoys the following properties. Zero. V evaluation. Then V has the following properties. Number one, V is quasi-local. And remember what that means is it's got one and only one maximal ideal. Two, V is interval closed. Three, every overring of V is again a valuation domain. Four, every overring of these localizations. And in fact, it's even stronger than that. It's a very good localization. Five, V is Bezier. And what I mean by that, I think I've introduced this, but just in case, every finitely generated ideal of B is principal. So it is the, possibly, not Noetherian analog for principal ideal domain. Six, all prime ideals of V are linearly ordered. What I mean by the statement with the prime in parentheses is I mean all ideals are linearly ordered. Therefore, all prime ideals are linearly ordered as well. That's actually worth knowing. And seven, if I in V is an ideal, then the radical of I, which we've learned from our homework, the radical of I is the intersection of all primes that contain prime. So from some of these properties, we can see the valuation domains are very specialized. Of course, you know, again, given an arbitrary pair of elements, one of them divides the other. They always have to be quasi-local. This is not sufficient. There are quasi-local domains that are not valuation domains. It has to be integrally closed. This is not sufficient either. There are integrally closed domains that are not valuation domains. Every overring of V is again a valuation domain. That's, well, I mean, it depends on how you want to generalize this. But certainly, for example, UFD is not characterized by, it's not true that every overring of a UFD is a UFD. There are some types, for instance, is true proof domains, PIDs, et cetera. Every overring of V is a localization. This almost never happens, in general, for a domain. But this is also not sufficient because every overring of PID is a localization. And most PIDs, for example, the integers, are not valuation domains because the integers is quasi-local. These Bezier, all prime ideals are linearly ordered, or all ideals are linearly ordered. And finally, the radical of any ideal is prime. Now, let me recall for you. Have this theorem. Gotta look, sometimes of course I get a little excited. I prove theorems earlier than I originally meant to, but I have this theorem here, later. That didn't matter. So let me recall. And by the way, if I'm using the word recall incorrectly, remind me. So recall that V is a valuation domain. If and only if V is a quasi-local Bayesian. I believe I proved that earlier when I first defined valuation. So in other words, this is not sufficient and this is not sufficient, but if you put 1 and 5 together, they are sufficient to, for the domain to be evaluation domain. We also constructed earlier some valuation domains, of course, Z localized P, formal power series ring over a field and one variable is valuation domain. I also constructed higher dimensional valuation domains and a one-dimensional valuation domain that wasn't Ethereum. By the way, since getting kind of the theme here, we've shown this, so let's kind of take stock of what we've done already. We've shown this, and we've shown this, and in fact, we've shown that, so we've shown the equivalent of these two. Every overring of a valuation domain is again valuation domain, it's localization. That's going to kind of come up later. And so the homework, I want you to think about this. How about 6 and 7?
Well, 6 immediately implies 7.
Okay, I buy that, but why? Can you give me a little more?
Because I is contained in any maximal ideal, there's only one maximal ideal. So we have there, it is contained in a chain of primes somewhere, basically, like, how do I put this?
I think you're on the right track. Why don't you look at the collection of all primes that contain I? Yeah. And what do you have? You have to have a chain, because the chain, because it's linearly ordered. And so the radical of I, so following your idea here, the radical of I is the intersection of P such that P contains I. And what did we learn about the intersection of the chain of primes? Is prime. So you are correct. 7 follows mistakes. That is correct. And I believe that I also showed that all the ideals are linearly ordered as a corollary of that. That means all the prime ideals have to be linearly ordered. I want to explore this one though. This one's one that I want to kind of, why is the interval closed? And this would be kind of a nice application of something we've seen before. Let me first, so this technique is actually going to come up later. So I think it's worthwhile for us to look at this just for a moment. Note. P is a valuation. And I think I may have told you this earlier, but let's see. P is valuation domain. If and only if for all P is quotient field, and you take a non-zero element, either omega or omega inverse is in B. So valuation domain means is characterized by take any non-zero element of the quotient field. It's either already in V or it's reciprocals in there, right? And this is just us. And I went and erased it, but this is just if you take any 2 elements of valuation domain that are not 0 and consider omega to be A over B, because after all, any omega in the quotient field is not 0, can be written as a quotient of these 2 elements. What do we know? Well, we know either either B divides A, in which case omega is already in B, or A divides B, in which case it's reciprocal, isn't it? Right? So this is just pushing around the original definition of valuation. So everybody cool with this? Now, line are close. Suppose omega in K, again, the quotient field of B is integral. Oh. So suppose we have some element, and I guess I should assume it's non-zero. Definitions. because after all, zero is certainly in B. Okay, so suppose I walk up to you on the street and I give you some element of the quotient field that is integral over V. Now, according to what I had up there on the board, that should mean that omega is in V. So how do we prove that? I think this is definitely not a situation where it's optimal to sit here and write down a bunch of polynomials, right? So, we'll call this omega inverse. You remember what the condition is?
Finitely generated.
No, something more recent.
More recent.
Right? So, and of course, clear that purpose. What's up here in white was the original statement of the theorem. State. Can somebody now tell me why the V has to be integrally closed?
Well, if we suppose that W omega is not in B, by this, omega must be in B, because omega inverse is in B.
Right. Let omega be integral over V if omega and V been done.
Yeah.
Right? If not, then omega inverse is in V, right? Omega is integral over V, which implies that omega is in. Because since omega inverse is already in V, then V adjoint with this is already in this. So no matter how you cut the cake, omega is in V, right? So V I'll end up talking about this later, but I can't resist this juncture. I can't stop myself. Since we're talking about this, let me also point out so I'm gonna write this as the side. Let R domain. I was quoting from the K. This is a quick aside with a little historical note too. Domain. How many of you have heard of the terminology almost integral? We have too many adjectives in that person commuted out, I think. How many of you have heard of almost integral? So you know what integral means, right? But almost integral. We say omega in K is almost integral over R if there exists non-zero R and R such that R omega n is in R for all n in the natural numbers. So in other words, if you can find, I like to call this element R an anchor obviously zero hitting anything, zero is cheating. So we say that there's a non-zero element that absorbs every power of omega and sucks it back down into R. Okay? This is a crappy definition if it isn't the case that every integral element is almost integral, right? But it's probably not completely clear, but I'll leave that as an exercise because we're going to talk about this more in the future, right? But it turns out that every integral element has its property. It's almost integral. There are elements that are almost integral that aren't integral. However, your domain has to be not in the theory, right? If R is in a theory ring, there's no distinction between these. And this is my historical note. For many years, I don't know how many it is, but there was some confusion in the literature over a number of years about the almost integral and integral. So anything that is integral is almost integral. And there were at least one paper that is known that was written under the assumption that these two concepts are the same. They are the same over in the theory and ring, but they are not the same in general. And I think actually it was in Noter that pointed out that this is different. Yes.
So, the first example of almost integral that is not integral is relatively new.
Well, I mean, last 100 years, relative.
Yeah, but also when we say that at least one paper made that confusion when we were talking like.
This is the 20s, maybe. I'm not the greatest at history, actually, but I think that was basically the time frame there. Yeah, it wasn't like the 70s. It was much longer ago than that. So just for fun, because you know this is going to come back to you anyway, see if you can prove that anything's integral is almost integral. See if you can find examples. But the reason I bring this up, I'm not completely having a stroke here, is I've got to add to this the domain R is completely integral closed. This is to the notion of integrally closed as almost integral is to integral. So the domain is completely integrally closed if it contains all of its almost integral elements. So in other words, if everything that's almost integral is already in there, then you're completely integrally closed. So if you're completely integrally closed, if you believe all this stuff I've been telling you, you have to be integrally closed. Right? And there's a large set of niceness to this. Every unique factorization domain is completely integrally closed. There's large classes of domains that are very nice with this respect to property. But there's a couple of weird things about it. Number one, if you take a domain and take its integral closure, the integral closure is integrally closed, right? So you take the integral closure, you're stuck. You can build domains that are not completely integrally closed and take its complete integral closure and it's not completely integrally closed. And you can make an infinite chain of things where it just keeps its mass. And here's the thing. This is why I bring this up now. We've just shown that if you're a valuation domain, you're always integrally closed. Valuation domains are almost never, in some broad sense, they're almost never completely closed. So that's a good example, that's a good place to look like. So in fact, here's kind of a theorem. Valuation domains are completely integrally closed. Yeah, and only now they're I'm struggling with pronoun evaluation domains. Evaluation domains are completely interval close if and only if they have, dimension less than or equal to one. So in other words, all non-zero primes are maximum. So only the smallest valuation domains in a certain sense can be completely interval closed. Fields, dimension zero. Or the examples that I gave you earlier that are one dimension, power series ring over field, in one variable, Z localized at P, or I gave you, some more interesting, I gave you a non-Noetherian, valuation domain of dimension one. These are all completely closed. But if the dimension, if you can stack, if there are two or more non-zero prime ideals, this thing is never completely integrally closed. It has almost integral elements in the quotient field, that are not in the domain itself, but all valuation domains, all of them are integrally closed. Here is a result. Here's a result that we will need very soon for a big theorem about valuation domains and their interplay with integrality. But this one is more general, for a general integral domain. Yeah, in fact, you don't need to be domain. Well, R inside P being commuted rings with one, and let U a unit in T. Basically, I'm trying to avoid U being a zero divisor. If I and R is a proper ideal, then I survives in RU or RU inverse. So right. Sounds like we're being really brutal to our ideals today. What does it mean for an ideal to survive? So before I prove this, let's make that if R inside T are rings, commuted rings one, so and I in R is proper ideal, we say I survives in T if IT properly contained. So in other words, when I lift an ideal up to the bigger range, it remains a proper, honest to goodness ideal, right? So let me give you an example. If you have, let me give you a silly example first. My silly example is if you have Z inside Q, only zeros. Because if you have, what do the ideals of Z look like? They look like N times Z. And if it's not zero, it's N is, we'll say it's generated by an element 2 or greater. When you lift that up to Q and look at that, well, Q's a field. And if that set's got a non-zero element in it, then you've got one in it and you're done, right? It's all Q. In the extension, let's say Z inside of Z localized P, can you characterize the ideals that survive?
You know, it's like,
Yeah, but there's more.
It's where all powers.
all right.
Right, the ideals down here. Actually, the surviving ideals are of form NZ with P divided N. Right, that's, and notice that covers zero as well. Right, so for example, if P is 3, and you look at the ideal generated by 5, it doesn't survive. But the ideal generated by 6 does. Okay. So what this theorem says is if you have R and a proper ideal I, then when you expand R U, or if you expand to, well, I guess it should contain a little more, shouldn't it? From a, or RU inverse, then in one of those two rings, if not both of them, this has to, when you lift it up, it has to be a proper ideal. So let's prove this. If not, so we'll not. If not, then we get two equations out of this. So let me write the equations down and kind of talk about what they mean here. A0 and B0 goes with AI and BJ, these A's and B's, with an I. Right? Because when you lift, what does a typical element in IU look like? Or, I'm sorry, RU. Well, this is just like polynomials, pretty much. So a typical element of this ideal, when you lift it up, should be a polynomial in U with coefficients from I. That's where this comes from. So this has to work for the U. For this to blow up, there has to be a linear combination, coefficients in I, powers of U, that equals 1. Right? That ideal has to take 1. And there has to be an analogous equation for in the powers of U inverse, right? So that's what it means to, by the way, sometimes it's very kind of bloodthirsty terminology. We say oftentimes that if an ideal doesn't survive, it blows up, right, to the whole ring, right? And to blow up here, you have to have a 1 in the extended ideals. So let me make a couple of, so I'm going to get sort of a minimality contradiction here. We assume chosen as small. and I certainly could do this because if n happens to be smaller than m, I just replace the rows of u and u.
Are chosen small.
No, what I do is, whichever one of these equations turns out, I assume that this one, and what I mean, I'm choosing n as small as possible, right? Among the positive powers, right? It doesn't matter, I can work this proof with the negative powers, so.
No, but I'm asking about m. M has to, cannot be as small as possible. I mean, doesn't have to be as small as possible. M.
No, it just has to be smaller than n.
Oh,
Right, yeah, as long as n is smaller than n, I'm good to go. Okay, so what I'm gonna do is I'm gonna manipulate this here. I am going to first, I'm gonna multiply the second equation. So this is equation 1, this is equation 2. Multiply 2 by, 2 by u to the and I'm gonna do a further manipulate this. So notice I get a un times b naught and a un times 1. So I'm gonna bring up b0 un over here. So I've got 1 minus b0 un is equal to this garbage that's left over. B1 u to the n minus 1 plus b2 u to the n minus 2 all the way up to bm u to the n minus m. Everybody okay with that? And now I am going to multiply the second, or multiply the first by 1 minus b naught. Right? That's lovely. So I am going to get, naught is equal to a n, 1 minus b naught un plus a n minus 1, 1 minus b naught, n minus 1 plus a2, 1 minus b naught, u2 or u squared plus a1, 1 minus b naught, u plus a0, 1 minus b naught. Everybody okay with that? Now, what I'm gonna do here is, see that piece right there? I'm gonna replace this. Useful. Previous equation. So I'm gonna get something like this. I'm going to get 1 minus b naught plus or equals an times this garbage here, which is b1 un minus 1 all the way down to bm u to the n minus m plus what's left over a n minus 1, 1 minus b naught, u to the n minus 1, all the way down to a0, 1 minus b. Everybody okay with that? Now, bring your b naught over here. Somebody quickly tell me what the contradiction is. This is equation like equation 1 with degree no more than n minus one, which is a contradiction to our limit model, because this is supposed to be the smallest degree equation involving you. You can see all these powers here are n minus one or less, and it might even be lower if there's some cancellation in the top terms. Okay, any questions on that?
I mean, I think it's trivial, but we don't need that the degree is bigger than zero. I mean, at the end of the day, it's the degree is zero, that means that A0 is one and well.
Right, that's right.
But do we need to do that clarification in order to do this process?
So if the degree. Right, so what you're saying is, if the degree is zero,
No, of course, if the degree is zero, we are done, right? Because we have
Uh-huh.
one in the ideal, but I don't know, I was just asking in order to do
Well,
all
okay.
these manipulations, we need to say, okay, notice that n is bigger than zero.
well, so what would happen here, if the degree up here was one, you have A0 plus A1U equals one. Right, and you would have B0 plus B1 U inverse is equal to one. Right? And yeah, so what you can do is you proceed with this reduction, and it's gonna be an equation just like this, but now what you're gonna get is one is a linear combination of the A's and B's, which are elements of the ideal I. So now you've got one is a linear combination of the A's and B's over R, which means the one that I was in a proper ideal.
Yeah.
Okay. Other questions? Questions? All right, well, think about stopping by the math club. Otherwise, we